exactly what you think. Measurement, usually in a math class, when they talk about measurement, you think, okay, what's the math definition of that? You know, you hear a word in a math class, it's like, all right, I know what that is in real life, but what is the unnecessarily complicated math definition of that? You know, this isn't that. It's exactly what it seems like. You're actually measuring something. Right? So, but the precision of the measuring instrument is the key component. Right? So the more precise your measuring instrument is, the more accurate your data will be. Right? So I kind of equate it to the idea of, you know, if I'm going to count how long it takes a person to run one lap around a track, I can do it by, you know, the old Mississippi approach. 1 Mississippi, 2 Mississippi, 3 Mississippi. That could be accurate, I don't know. Depends on how fast I say Mississippi. It depends on how I enunciate. I remember when we played touch football back in the day, Mississippi became Mississippi, just because you wanted to get to that quarterback a little quicker. So there's a lot of little ways that you can kind of finagle that. But if I use a stopwatch, it's going to be more accurate. Right? It's a more precise instrument. If I use an atomic clock, it's going to be the most accurate. Right? So there's a lot of variables at play. Same thing with scales. Like if you're weighing something, if you're weighing it by comparison, for example, you know, like, no, actually, let me go with height for a second, because one way that I count out my handouts for different classes, and I've done this for years, and it only rarely fails me, is I count out height comparatively. So I'll get a stack of papers that I know has a certain quantity in it. Okay, so this is about 10, I believe it's 10 packets, okay, each with 2 pages in it. So that's 20 pages. So if I need to count out 20 pages for another class, what I'll do is, I'm not counting it, I'll just put a stack of papers there and just do this. Yep, about the same height. And then I'll just do it. Yep, about the same height, about the same height. That takes me about 10 seconds as opposed to 1, 2, 3, 4, 5, 6, 7, you know. So is that going to be precise? It'll get the job done, but I don't think anybody's going to say it's going to be precise. And the precise way to do it would be to actually count it out. Same idea for weighing things. If you're weighing by, you know, like you could use just a scale at home versus the scale at a doctor's office as a basis of comparison. Something simple. You know, maybe the one at home is more accurate, but one is probably more accurate than the other. Right? When it comes to linear distances, it's about the tick marks and how close they are to one another. Right? The closer the tick marks, the more precise your measuring instrument will be. All right, so here I'm just looking for the measure of segment AB. So as we go through this, we're going to talk about the notation, and we're also going to talk about, you know, actually answering the question. But the notation ends up being an important piece to all of this. All right, so the M, the lowercase m, stands for the measure. Let me make a little note of that. Oh, sorry. This other piece is the segment, the line segment AB. All right. The segment, and I'll give you your papers back from last class, but a line segment is just, it's just a portion of a line. Doesn't extend forever. It has 2 finite endpoints. All right. So that's something that's measurable. If there was an arrow on one of the ends, it would not be measurable. All right. So this, if I said I have line L here, and I said, give me the length of line L, that's either a flawed question on my end or it's just a trick question. All right. You cannot find the measure of line L. So the measure of line L, we put an arrow over the top of it, a double-sided arrow. Line L would be no solution. All right. Or you could say it's infinity. Right? Because it never ends. It extends in either direction forever. You could measure from the tip of this arrow to the tip of that arrow, but all you're doing is giving me the length of that one line segment. Right? It's just one tiny portion of that entire line. Right? So the notation gives us a sense of what we're being asked to figure out, but also, you know, it helps us to avoid falling into little tricks and traps and things like that. Right? So in this case, you know, the best you could do is just kind of eyeball it. It looks like it's right around that 2.5 mark. So, you know, you can count little tick marks if you want, but I could say just 2.5 because here's 2, here's 3, this looks like half the distance. All right, so I could say 2.5, 2.5. So I'm going to write all these possibilities. You'd only have to write one of them. 2.5, 2.5. I could also count up the little tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 in total, and I've accounted for 5 of them. All right. So I could say 2 5/10, but really that would just become the 2.5 anyway. All right. When we get to the precision of a ruler, we're talking about what the distance is for that first tick mark, or the distance between any 2 tick marks. All right, any 2 tick marks. All right, so we're basically just looking for that fraction that we just came up with. All right, it took 10 tick marks to get the whole way. So each one of those tick marks would have to be 1/10 of the distance. So the precision of the ruler is 1/10, or you could say nearest tenth. All right. You could go by half units, half tick marks, but that becomes a little bit more challenging because sometimes it doesn't look like, if you went by where the edge of that circle is, maybe you'd say it's like 2 6/10, but I was looking at the middle of the circle down. You could go even a little bit further and say, well, maybe it's in the space between the 2 tick marks. But where in that space? Directly in the center? I don't know. So what we do is we go to the nearest tick mark, which in this case means that we're going to the nearest tenth. Right? So this is the basis of rounding. This is where it all comes from, just knowing what the precision is. Rounding and precision are the same thing. Right? So when we look at number 2, we're measuring this pencil. There's less tick marks. They're more spaced out. The first one was in centimeters. I didn't write the units because it was right here, but I suppose we probably should, just for consistency. I'll just chuck in a little cm. I'm not in the habit of taking off credit for things that are common sense. Okay. But we're a little bit more than 2, so we know that we're 2 and something. There's 1, 2, 3, 4 tick marks separating each integer value. All right, so that would mean that each tick mark is going to be 1/4 of a unit. All right. So specifically 1/4 of an inch, but really that's telling us that we're going to round to the nearest quarter unit. So specifically 1/4 inch. All right, so when we get to the length of the pencil, that's putting us right here, that's going to be 2 1/4 inches. Or 2.25, however you want to do it. If you want to put it as an improper fraction, you could. That would be 9/4. I don't see why you would want to do it that way. It's less intuitive, but I suppose you could. All right. And so the next one, measure of CD. Again, measure of the line segment going from C to D. All right. So these are centimeters, but again, we count the tick marks. It's a reasonable assumption that if you're working with centimeters, that the tick marks would be millimeters, but you never know. You could break up an interval over, from integer to integer in any way that you want. All right, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are millimeters. So 1/10 of a centimeter is the precision of the ruler. And so the measure of C to D would be what? 5.5. 5.5 centimeters. Now again, a fair amount of this is, like I said before, it's stuff that you already know. It's just we're kind of, in many ways, it might seem like we're being probably more specific than we need to be, but there's a reason for it, because if we get the terminology down, then when we have to try to prove some of these relationships, it becomes a whole lot easier. All right? So, yeah, common sense tells us, well, that's half a unit, so 5.5. But the rationale is because there's 5 of those tenths. All right? That's our distance. All right, so in number 4, what's the precision? What's each tick mark worth?
That's
16, 1/16. Right, so if you're going from 0 to 1, you count up all those tick marks, there's 16 of them. All right, so the space from one tick mark to another would be 1/16 of an inch. All right, so going from E to F, we're looking at 1 and how many of those 16ths?
11.
That looks like 11, yeah. All right, so 1 and 11/16. All right, and it's pretty commonplace that when you're working with, I was just going to say when you're working with like tools and stuff, but really, I mean, anything that requires measurement, that odds are you're going to be working with 16ths and 8ths and 4ths and stuff like that at some point. Trying to think, I just hung up it's a rack, a wall rack for pots and pans and stuff. 2 of them. I did some measuring like this. I mean, it wasn't complicated. I didn't have to actually take note of what the numbers were. Like if it were 1 and 11/16 or 2 and 3/8, I wouldn't have known. All I knew is that I was going to hold the ruler at this distance and then measure that same distance. I think I did 18 inches down, so that I could make the mark for the next drill hole. So, there's ways around it where you don't have to consider the numerical values. You just need the position, but it's good to know anyway. And also, the precision, again, dependent on the device you use, it could be vastly different. Where is it? This probably isn't going to work on the, I could probably do it here. Okay. Yeah. There'll be a little glare on it though. You'll survive, you'll get it. Geometry. Oh, only 7 people on Remind? Where is number 8? What if I was late tonight? You wouldn't have known. All right, so you got that. All right, you see. So when I measured it on there, I mean, it's a picture of a display that's not drawn to scale. So I did not expect it to be 1 11/16 inches. But if you did that on your own paper and it was drawn to scale, maybe you can get that actual measurement. All right, and I rushed it, so it's a little off, but you know, it came back with 5 centimeters. So the measuring device is definitely specific, is going to give a value that's specific to its level of precision. All right. So, but if I tell you on a test or a group assessment, more so group assessment, not so much test, but if I tell you, oh, here's an example. The first one that you're going to do later is going to ask you to determine the length, the diagram will be drawn to scale, the length, and determine the level of precision. And if you use your phone to measure it, right, and if you have an iPhone, you have this app, I believe it's called measurement. What is it called? Measure. Then it'll bring it up for you. I don't know if the angle one is native. I don't think it is, but there's an angle app that I downloaded also that'll do that. But there's lots of little features that you can use on your phone that'll get these values. Just out of curiosity, let me just see what it would be on the paper. Of course, it takes a little bit of used to. Oh, okay. Well, on the paper it says 5 centimeters. Oh, I did not know this one had a level built into it. There was a way to change the units, I just can't remember how to do it.
You click on it, I believe. Once it gives you the first measurement.
Oh, tap on the number?
Yeah.
Or the icon?
Oh. Yeah, it gives you inches and centimeters.
Oh, it does, okay. Oh, the little arrow. Oh, approximately 2 inches is what this is coming back with.
Which one are you measuring?
The one that we just did, number 4.
Oh.
So yeah, 2 inches, all right. It's a little on the long side. Usually I brought my other bag, but if I had a regular ruler, you could just actually measure it. It might actually be about 2 inches because it's not drawn to scale. That's why I have the ruler below it. You know, so it is totally based off of the type of device that you're using, right? So when I ask you to measure something, and it's in the form of a group assessment or something like that, phones are fair game, right? But if it's and basically, let's just put it this way: I'll tell you when you have to put the phones away, all right? Otherwise, you can have them out. So the apps and stuff like that that are built into your phone, or even ones that you download, you're welcome to use those, all right? So number 5. What does MCD mean? Well, we wouldn't have got this far if we didn't really have a sense on that. That's saying that the measure of line segment CD is 1.25 inches. Now, we all have varying backgrounds when it comes to some of this stuff. So some of us have seen a fair amount of geometry before, some of us have seen none of it. All right, so I have to kind of assume that we're all on the floor, on the ground level. All right, so, and that's the way it is. That's how I teach every class. I can't assume anything. So in number 6, you see that little equal sign with the tilde over it? All That's a funny looking symbol. That stands for congruent. Congruent means geometrically equal. All right, and it seems like kind of splitting hairs, but without that little M in between, in front of a segment, we can't say that the segments are equal to one another, because equality only deals with numerical measures. Congruence deals with being the same without accounting for numerical values. All right, so I could look at two line segments and say that they are congruent based off of maybe properties of lines, maybe some other relationship, or maybe because somebody flat out told me. But once I measure their lengths and establish that those lengths are equal, then what I'm saying is that their measures are equal to one another. All right, I've moved away from congruence and I've moved more towards equality. All right, so, and like I said, it seems like splitting hairs. Like, what's the difference? It's basically the same thing. What it allows for is basically context or contextual situations to allow for two things to be congruent, so the same, but representing two different things. Because if you have two line segments that are congruent to one another, they could be representing two very different things. All right, we're only focusing on the geometry of it, but maybe one line segment is talking about the rate of change of an airplane's height as it takes off from a runway. And another is talking about the rate of change of a car as it starts moving from rest. All right, so it's at a stop sign and it goes into motion, and you have a line that represents that. You know, lines have slopes and y-intercepts and stuff like that. All right, those two lines could have the same distance, but maybe their number is not the same. All right, because one line could be in the units of miles per hour and the other could be in the units of meters per second. All right, so this line may have a number of 20 and this line may have a number of 500, but they're the same line. So the lines are congruent, but they're not equal. All right, it's only when we get into their actual numerical value that we talk about equality. All right, so basically that kind of opens the doorway to, all right, well, are we limiting this just to line segments? Well, it could be circles, it could be triangles, it could be three-dimensional figures. All right, you could have a sphere that represents one thing and a sphere that represents another, and they have two different values. So you can think of it this way: two spheres, one hollowed out and one solid. All right, you look at the spheres and you say that they're congruent because they're the same size and shape. But if I talk about the density, you know, like the composition of those two spheres, they're vastly different from one another. Like, one's basically a bubble floating through the air, and the other's a ball bearing that if somebody threw it at you, they'd kill you. You know, so it has to do with the quantity as opposed to just the look and feel of it. All right, so the second condition there, they're telling us that CA and BO, it's usually CA and CB, are congruent, but then they tell us the measure of CA. Now we're changing the narrative a little bit. So if the measure of CA is equal to 0.6 centimeters, now I'm talking about a linear distance. So all those crazy examples that I gave about cars driving and planes flying and spheres that are either filled in or not, those don't apply. We're just talking about the length of a line segment. Right? If that's the case, and I know that those two line segments are congruent, as in their shape is the same, their distance is the same, then we can conclude, I'm going to draw three dots in the form of a triangle. That means, therefore, the measure of BO is equal to 0.6 centimeters also. I think I got a little lazy when I was typing this up. This should actually say the measure of segment BO. And this one down here is ME. That should say the measure of segment ME. I talked to you about typo bonus yet? Getting bonus for typos. So there's 2 of them. So all you have to do, if you want the bonus points, you can max out at 3 points. All you have to do is identify the typo, and just because I corrected here doesn't mean that the opportunity is off the table, because I need to correct it in the master document, right? So I still need somebody to submit this, otherwise that typo will stay there forever. So just send me a message on Remind saying page 1 of, in this packet I'll know what you're talking about, we've only had the one. Number 6, change BO. I'll know what to change it to. All right, there's an element where you got to kind of have faith that I'll know what you're talking about, but I just need the reminder to open the file and make the edits. That's more than anything, you know. Because I've had people that, like, they would send it like an essay. Like, on page 1 of the angles and measurement packet, referring to the congruence example with, the one that involved the airplanes, and it's like, oh Christ, I just needed to know to change the BO, so yeah, just quick and easy. All right, so along the same lines, we know, so TI and ME are congruent, so that means that their measures are going to be equal, all right? Because we're talking about linear measurements, all right? So the distances are, what's that question here? We're not talking about density, we're not talking about temperature, because if we're talking about temperature, one could be in Celsius and the other could be in Fahrenheit, like it could be apples and oranges situation. Here, we're talking about a distance. There's no reason why we can't use the same units. I suppose if you wanted to be a wise guy or gal or whatever is appropriate in the 21st century to say, you could convert it to miles just to mess with me. I'll go over that in a minute. Because unit conversions are pretty convenient, or allow for convenience. And so definitely something that you're going to want to attend to. All right, so the remaining problems here, they're all pretty basic because they're relying on some piece of given information and you have to draw a conclusion based off of that. All right, so in number 8, we have 2 measurements from A to B and B to C. All right, so again, it seems like, and I promise you it's not for the hell of it that I'm doing this, but it'll seem like I'm making something that's really easy into something way more complicated. It is not that. I mean, don't get me wrong. I have taken the scenic route when teaching certain concepts before, like just because of the way my brain works, but that's not this. This is so that we could learn properties while also being grounded in familiarity. So what we're going to do here is we're going to take, to get from A to C, we're going to take the sum of the measure of segment AB and the measure of segment BC. All right. This is what's known as the addition postulate. Geometry has some words that you might categorize as of the made-up variety. It's just something you got to get used to. And that's why when I do my assessments here, it's for, like in the group environment, and I try to do it that way, and more err on the side of projects and presentations specifically for geometry, because there's a lot of rules to know. They're not all intuitive, and the ones that are intuitive usually have some crappy name that you're like, oh, it's addition. I'm just adding two things together. Why do we need to have the word postulate there? Because somebody decided 1,000, 2,000 years ago that had to be there. We'll talk about axioms and theorems and things like that. The one that you might find to be most familiar is property. And that's a good one. Okay, fine. We got something that's familiar. I can give you the gist of the definition of postulate, but I'll just give you the, I wanted etymology, not definition. Well, while it's here, I'll read the definition. Suggest or assume the existence, fact, or truth of something as a base of reasoning, discussion, or belief. All right, so it's a truth. So it's the addition truth. But like I said, I meant to look up etymology. All right. From Latin, meaning a demand, or from the Latin postulatum, a demand, request, properly that is that which is requested. All right, so actually this is one of the cases where the actual definition played out a little bit better. Yeah. I mean, that didn't really add too much to the plot, but really it's just some kind of an assumption or something that's assumed to be true. But the reality is, in this case, all we're doing is we're taking the 16.7 and adding to it the 12.8. Ideally, you would add those correctly. There's no need to add anything by hand. You're welcome to use a calculator. I don't have a particular requirement of any kind of calculator. If you're looking for one of a graphing variety, the X84 is pretty good, but so is this. The one that comes with your phone, so 16.7, 12.8. 29.5, yep. And that would be millimeters. All right, units are going to be a big deal. Really, I kind of decided yesterday that the only two things that I ever get nitpicky about are labeling graphs and units. Everything else is like, I know what you meant. Like, it really is that. I mean, addition, postulate, if you forgot the postulate, I'm not going to lose sleep over that. I mean, again, there's what is ideal, and then there is, have you demonstrated knowledge of the concept? The things that make me lose my mind are not labeling graphs and units, and not including the units, because those are necessary pieces of information to tell the reader what you're talking about, right? It would be like me walking into a classroom and, I'm just going to start teaching. Just day one, start teaching. I'm not going to identify myself, not going to say what the rules are of the class. I'm not even going to check to make sure I'm in the right classroom, right building, right school. I'm just going to walk into a room, start teaching. The thing that would make it appropriate for me to teach would be to identify myself as the teacher, and then also make sure that I'm in the right place. All right, so the units are the identifier, and the labels on a graph would be indicating that you're in the right place. So those are things that I'm very picky about. Some people care less about that, right? But I care a very great deal about that. Right. The next one, we start off with the 4.0. That's the whole distance. Part of it's 1.2. The other part is what I'm looking for. So what I'm going to do here is I'm going to take the measure. I'll do that in a different color, actually. The measure of RT and subtract from it the measure of RS. And what do you think the name is of that postulate? Subtraction. In a couple weeks, we'll be using these postulates and properties and theorems and axioms without any numbers. All right, we're going to be given a set of assumptions, and we're going to have to draw conclusions based off that. We're going to learn a little bit of logic along the way, just because that's a kind of an important part. And also, I've discovered over the years that people think that their reasoning is logical, but it isn't. All right, so 2.8. So 2.8 centimeters. Yeah, what ends up happening is people confuse logic with making sense. Well, that makes sense, so it must be logical. Well, sometimes logic doesn't make sense. All right, logic is the sense, but sometimes it doesn't feel right. I'll just give you a quick example. If I were to say that I am either wearing blue jeans or a gray shirt today, would you say that that is a true sentence? Make it better for you. I am either wearing blue jeans or a gray shirt today.
Would that make sense? Yes.
Yeah, is that a true sentence? Yeah, because as long as I'm wearing one or the other, I'm good, right? But that the gray area, no pun intended, is if I'm wearing both of them, because sometimes people think when there's the either or that it's a choice. It's one or the other, one exclusively of the other. So if I'm wearing both, most people, and by the way, if you think it's a true sentence, that you're logical minded. If you thought it was not a true sentence, we have a little bit of work to do, because the logic tells us that it's true if I'm wearing either of those two things. If I'm wearing both of them, it's double true, right? The only way it would be false is if I were wearing neither of them, right? So if I were wearing like red pants and a black shirt or something like that, it's not my style, but that's the idea. So we got to train ourselves to think logically, because that's going to allow us to combine it with the geometry and be able to make some meaningful conclusions. All right, so then WX in number 10, seems like we don't quite have enough information, but if you count tick marks, you can kind of see that we have exactly the right amount of information. All right. All right, so this X cuts that distance in half. All right, there's two tick marks separating it from W, the X from W, and then there's two tick marks separating the X from Y. All right, so it's what we call equidistant. All right, so X is equidistant when I first heard that word, I was like, can he not say equally? Like, is that like a tongue twister for him? Like equidistant? I thought the teacher was just saying it fast. I'm like, you sound stupid, dude. Just say it. Say it slowly. You'll get it. Just try. No, it's a word, equidistant. Some people pronounce it equidistant, right? Just because they don't want to sound weird when they say it. I think saying that sounds weird, so, but that's just from experience. From both W and Y. All right. And so what this is, and by the way, definition of equidistant is equally distant from. So it's like, well, why couldn't you just say that? I don't know. The geometry gods made a choice. All right. So x is equidistant from both W and Y. So what we say is that x is x bisects the line segment WY. And again, this is all like, you might look at it as unnecessary, but I look at it as absolutely necessary. Because when I give you a problem that involves you having to explain using properties of geometry, and then I say you could use your notes, and you have this written down, and you could flip right to it, and you say, oh, there it is. We're good. I got it all right here. You just got to know where to look, right? So x bisects, and again, it seems like completely unnecessary because you already know the answer is 2.4. Why are we going to do this? We're trying to learn through the process, all right? Grounded in familiarity, all right? And so what this is the line bisector property. All right. We're also going to have an angle bisector property down the line. So, but you know, you'll learn what a bisector is at one point. You'll know what it is for everything. It's just going to cut. It's going to be an object that cuts another object in half. All right, two equal pieces, making it equidistant from those two other pieces. All right. So if you kind of look back on what we just did on this sheet, it really does look like I took, we'll call it 4th grade math, and just made it like way more complicated than it needed to be. But again, I promise you it's for a purpose. I always tell people that, you know, especially in my calculus classes, you know, because for a lot of us, the math journey is ending after this semester, and for some of us, it's much longer. And my calculus students, it's just beginning. You know, they got years after that. What they do, and the same thing with statistics, is if you're going into a field that involves math, like engineering or just pure math, usually what happens is you take all the calculus courses, you finish all those classes, and then you pretty much start them all over again. This time, learning the origin behind everything, right? Which is kind of weird to think about, because what happens is, I'll take statistics as an example. You learn a bunch of formulas, but they're just given to you, or you just have to memorize them. The second wave of that education involves you understanding where those formulas come from and why they're important, right? So that's where we are for measurement. We're trying to kind of circle back to all the things that we took for granted way back when, and understand why they exist and in what way that they can help us. And that's gonna be kind of largely a theme of the course, all right? Number 11, point B is between points A and C. So it's basically asking us to do the same thing. It's just it didn't give us a picture. So what we do is we just draw a quick diagram. Gonna have to do the same thing for number 12, so I might as well just draw 2 line segments. All right, so point B is between points A and C. So I'll put point A here, I'll put point C here. Keyword between. Does not mean in the middle. So I'll say does not mean midpoint. Mean midpoint. All right, because for whatever reason in the past, people have seen the word between and they have interpreted it as directly between, like right smack dab in the middle. Not necessarily the case. So AC is measured at 32 millimeters and AB is 17, all right? One of the things I am gonna ask you to do before it's all over is to draw a scale drawing or construct a scale drawing, all right? This is not one of those moments, but you do wanna sort of get in the habit of saying, well, I don't wanna put the B here, that wouldn't make sense. B is supposed to be 17 millimeters, all right? That's gonna be more than halfway between A and C. So halfway point, you just ballpark it and just go a smidge to the right of that and plot your B there. All right. Later on, we'll do it with measuring devices. We'll use phones, rulers, whatever. All right. So that distance is 17 millimeters. So now we have our diagram, and we want to use the subtraction postulate to figure out BC. So get in the habit of not only performing the operation, but also stating the reason why you were able to do that. So this is subtraction postulate. And there's no requirement that you have to set up an equation. I mean, one thing I always want you to keep in mind, whether you always remember to keep it in mind, I don't even know if that makes sense, but it's not an algebra course. So there really shouldn't be too many instances where you need to set up an equation and solve for x. You know, that's not why we're here. Most people, well, historically, most people are here because they don't want to take another math class. But there are some people who are like, oh, what's this geometry stuff all about? You didn't come, regardless of why you're here, you're not here to do the same old stuff that you've been doing, right? You don't want to be like, factor, solve for x. Create a graph of a parabola, see where it crosses the x-axis, right? Distribute, you know, like you want to do something different, right? So don't force yourself to adopt old habits. You know, just get it done, all right? So if it means doing it in your head, doing it in a calculator on the side, it doesn't matter to me, all right? Either way, one way or the other, you're getting 15 millimeters out of this. So that's all I'm looking for. But the justification is going to be the key ingredient, all right? So point C is between A and B. The same setup. Well, kind of. 3 points, one in between the other. Now, AC is 3 1/8. CB is 2 1/16. All right, so you're going more, you're covering more distance from A to C than you are from C to B. So it's another instance where you would want to err on the side of plotting the point to the right of where you suspect the midpoint is. All right. So 3 1/8 inches. Two 1/16 inches. Now, some calculators can handle fractions better than others. Some of us can handle fractions better than others, so it all depends. If you have a graphing calculator, there's a function in there. Most scientific calculators have a fraction key that you could use. If not, you just got to kind of suck it up and do it by hand. We will be using the addition postulate.
It says measurement of CB is 2 1/16.
Yeah.
It says find BC, that's the same thing.
Oh, typo.
Oh.
Yeah, it should be AB. Yeah, you got it. Good call.
Alright, so
Now, if that happened on a test, don't say anything.
Okay.
Just write 2 1/16 as the final answer.
Okay.
You know, because it could be a trick question, or it could be the bank making an error in your favor. Either way, it's a screw up on my part. So, but yeah, so it should be A to B. Thank you. Yeah, I always say, and you know, some classes it's more of an issue than others because there's more calculation involved. But if you spot an error, you know, whether it's a typo or I just flat out whiff and make a mistake, let me know sooner rather than later, because my classic example is in a stat class, we were doing standard deviation, and it involves you finding the mean, the average in the first step, and then doing 25 minutes of work after that. Okay? So I like the big reveal at the end where we check it on the calculator. So I did all the work, like got my answer, and I'm like, all right, now let's check it. Checked it, didn't match up, and I'm like, well, I screwed up. I guess we're gonna be staring at this problem for a while. And then somebody raised their hand and said, oh, you screwed up on the mean. You know, that first step I was talking about. And I was like, oh. And I was like, well, just out of curiosity, when did you notice that? Oh, like right when you made the mistake. I was like, oh, so you noticed the mistake 25 minutes ago, and you let me continue down this road. Please tell me you were doing that for the purpose of killing time in class. No, I just figured I must have missed something. Like, you're a teacher, you're probably right, I probably screwed up. I'm like, no, please don't take that chance. Because now we got to do 25 minutes worth of work again. You know, that's the horror story. That happened 15 years ago, and I've been telling that same story since. All right, that's how much that stuck with me. All right, so if you notice a mistake, say something definitely. All right, and especially in this case, because some of us would have went home and been like, all right, I guess BC is 5 3/16. Sounds about right. I guess he's a teacher, I'm sure he's right. But no, that would have been horribly wrong. That would have been terrible. So, addition postulate, we're adding A, C, and CB. And besides, I'm giving you points for finding my mistakes. By the way, there's a typo, so somebody can get typo bonus for that. If somebody's really on the ball, they'll already have their 3 typo bonus points for the semester, just from tonight, from my first handout. Don't worry, there's plenty to go around. I fix typos, and when I fix them, I make accidentally, not on purpose, I make new typos. I don't know what's wrong with me.
We all send the same.
First come, first serve.
Oh.
Yeah.
Oh, really?
Yeah.
All right, this is mine.
Well, you just got to duke it out.
That's a lot of work for you to smooth then.
Oh no, I just ignore all the ones that came in after the first one. But
So now it's like,
yeah, a little gladiator action going on, like duke it out.
Except screenshot.
Screenshots are fine, yeah. You'll know within 24 hours if you got it, because you'll either get a bonus point on Blackboard or you won't. I try to give a little thumbs up if you got it, but I forget most of the time, so that's of no help. But yeah, like I said, there's enough to go around. So like if you're always coming in, you know, just a little bit after the person who's getting it in, don't worry, you max out at 3 bonus points. So they'll be done. Somebody will be done tonight, I'm sure. That's one less person to worry about competing with. All right? So you could be the last person standing, but you'll still get your 3 points. I wish I could say I was making these mistakes on purpose. I have a friend at the high school that we call each other R&D, because my job in the relationship is to come up with what I think are brilliant ideas for instruction, like lessons, activities, things like that. And her job is to type it up and make it look nice so that I don't type it. She just doesn't want me typing it. Like, what do you think you do? Get away from the keyboard. You're gonna screw something up. If there needs to be an edit, the preference is that I tell her, and she'll take care of it, because everything that I touch in terms of a document, it just falls to pieces. I have kind of snuck a few edits in, but it never works out. So anyway, we're gonna add the 3 1/8, and we're gonna add to that the 2 1/16. Now, a little computational skills action going on here. It's like when algebra became a thing. Everybody's like, where are all these letters coming from? Why do we have to do this? Can't we just go back to numbers? And then we go back to numbers, and you're like, well, not these kind of numbers. They're like better numbers. I don't want fractions or radicals, you know, but we live with what we got. All right, so this is the same as 3 plus 1/8 plus 2 plus 1/16. All right, one of the properties, not of geometry, just going way back, properties of numbers, is the commutative property of addition. Tells us we can add in any order we want and we'll still get the same result. So I choose to add the 3 and the 2, then the 1/8, and then the 1/16. All right, because I can get a clean 5 out of this. Then I just got to worry about the 1/8 plus the 1/16. All right, so I need a common denominator. So if I want the 1/8 to have the same denominator as a 16, I have to multiply the top and bottom by 2. So that's going to be 2/16 plus the 1/16. All right, so then I can just add these two together to get 3/16. So we're looking at 5 plus 3/16, but then when we write that as a mixed number, it's 5 and 3/16. And it's been a while now, so I don't even remember what the units are. Inches. All right, not an algebra course, also not a computational skills course. It's a geometry course. So there's no reason why you'd have to do any of that by hand. It's just depending on what kind of calculator you have, you might have to. You know, so if it's one of the assessments that's no phone allowed, and you have a really cool calculator on your phone, it's not going to do you any good. All right. So if you're going to get a calculator, my recommendation, again, it doesn't have to be a graphing calculator. If you have a graphing calculator, that's fine too. But if you're going to get a calculator, a scientific calculator, make sure it has fraction capability on it, all right? Because we're going to do a lot with fractions in this class. All right, but those good old TI-84s, they have a fraction function built in. Like, you just type in the fraction just the way you see it, add to it another fraction, it simplifies it for you. It's all great. But I'm not going to tell you to spend $100+ so that you can add fractions, right? If you're going to take more math classes after this, different story, but generally not necessary. I had a thought, I was going to elucidate based off that thought. I forget. It's right on the tip of my brain. Unit conversions. All right. Sometimes, well, many times, I decide on the fly that I want to include a new topic or an additional topic into a lesson. I also take those as typos. All right. So it's not technically a mistake, but it's kind of like an error of omission. So what I'd like to have in here is a little section on unit conversions. All right. And so we'll have to find some space to write it. I mean, you have notebooks and stuff, but it looks like we'll just go right to the back of the last page. And we're just going to talk about converting in linear units for a few minutes. Okay, I forgot to not make typos and stuff. Okay. Number 17 and 18. Fill the space with either the congruent symbol or the not congruent symbol. By the way, any symbol that has a slash through it is just the opposite of the symbol normally is. All right, so you can make a note of that. Again, these notes are all for your reference during assessments. So the more notes, the more you mark it up, the better off you're going to be. So this means not congruent. All right, so if I had an equal sign with a slash through it, that would mean not equal. All right, so what we're going to do for 17 and 18 is we're just going to look at the measures of the two indicated sides. Here I can see that the measure of AB is equal, so this is a context for equal, to the measure of CD. They're both equal to 5 centimeters. So that's going to tell me that the two geometric figures are congruent. All right. Now, this actually has to do with properties of a parallelogram. And, you know, like before when we said the addition postulate and the subtraction postulate and the bisector property, we probably should talk about properties of parallelograms, but there's actually a whole unit in this course on quadrilaterals. So we can just kind of save that. NP and MP. So here's NP. And here's MP. Those two measures are not equal. So we would say that this is not congruent.